Hi everybody, welcome back to this lecture on microcontroller and its application. In the last lecture we discussed about PIC microcontroller and its basic features. We introduced the PIC microcontroller to you. In this lecture I would like to introduce a little bit more detailed features about PIC microcontroller. Basically its block diagram architecture and its internal registry features. So let's look at it in a little bit more detail. So basically your PIC microcontrollers are based upon an architecture called as Harvard architecture. Now, a Harvard architecture means your microcontroller accesses your program and data from two separate memories called as program memory and data memory. And it also has distinct buses for doing that. In the other microcontroller and microprocessors that you would have studied still now, you would have noticed that there was the same address bus, there was the same data bus to access both the data as well as the program. But not so with PIC microcontrollers. It has a distinct data bus and the program bus. It has different. So this facility greatly enhances the speed of fetching and execution of instruction, and this is what is called as a Harvard architecture. So it has a separate program memory, it has a separate data memory, it has distinct buses also for fetching program data as well as RAM data. So this makes the execution of program also faster. So that is the concept that is being used in PIC microcontrollers. Now, PIC microcontrollers also use the concept of pipelining in the fetching and executing of their instruction. Every instruction in PIC microcontroller is 14-bit word wide. 14-bit word wide. Okay, so each instruction when it is being fetched, as you can see, it will also get executed. As you can see in the figure over here, for each cycle, now PIC is a microcontroller which will try to execute every instruction within one cycle. So, and as you noticed, and within 1 microsecond, up to 5 instructions can be executed in a PIC microcontroller. So in a PIC microcontroller, whenever an instruction is getting fetched, it will queue the next instruction that has to be fetched, and it operates in a queue likewise. So whenever this instruction goes for execution, the next instruction that was fetched is in the pipeline already for execution. So whenever it is fetching one instruction, it is executing in another instruction. So this is what is called as instruction pipelining, and you would have seen this concept in when we studied microprocessor 8086. So this is what is called as instruction pipelining, when a particular instruction is fetched and another instruction gets executed. There are times when this pipeline will be interrupted, or instruction queue will be interrupted, and those are the times when you have an interrupt. Whenever an interrupt happens, the program counter, which holds the address of the next memory from where to fetch the program code, has to dump its address to a stack, and it has to retake an address from where the program code has to be accessed. So in such an event, your your instruction pipelining will actually reboot, or it will actually dump the queue. Okay, so this facility is available. So that is the time your microcontroller can little slow down. So in such an event, whenever there is an interrupt, it will fetch the new address, and it will change the program counter's new address into new address. Once it has dumped the old program counter value to a stack, and then it will fetch the new address and ignore the old addresses that were queued up in the instruction queue, or the pipeline, instruction pipeline. So that is how it actually processes. So uh, the PIC 16C74A, which we would be more uh, more detailedly studying, but the PIC family of microcontrollers basically have this block diagram or architecture, as you can see on the screen. Now we'll be not dwelling too deep into this block diagram, but from this block diagram or architecture we can see certain features of PIC microcontroller. As you can see on the screen, it has a ROM memory, we'll see how the PIC family of microcontrollers had different types of capacity of ROM memory. It has an instruction register, which of course fetches the instruction from your ROM program memory, and it has an instruction decode, which makes meaning out of that instruction that has been fetched, and based upon the instruction decode, it actually generates a specific control signals for operation. Now, apart from this, you have different oscillator options, which is connected to your timing generation unit. You have RC oscillator, crystal oscillator for more stable oscillator timings. So you have different oscillator timing settings, which you can select at your own will. You have a program counter. As you know, program counter is a register which holds the address of the next instruction to be executed. You have an 8-level stack. In an event of a jump instruction or an interrupt, you need a stack, and you have an 8-level stack. That means up to 8 interrupts can be serviced, and the program counter address can be put into a stack. And during that's why it has an 8-level stack. It has RAM, of course, RAM file registers. The capacity of RAM again varies from between different family of PIC microcontrollers. It has FSR register we will see in detail later. FSR is a register which is used for indirect addressing mode. Status is a register which you can find parallel with the flag register in the microprocessor microcontroller that you have seen before. Status is the register which has the carry bit and the digit carry bit and 0 bit, which are equivalent to which reflects the status of the program that is being running in your microcontroller. It has some integrated options like power up timer and oscillator startup timer, power on reset, washed out timer, brown out reset. All these are integrated options which are available with your microcontroller, which we will see later on much in detail. And of course, it has the arithmetic and logic unit, which is used for processing all the arithmetic and logic operations. In PIC microcontroller, it has a W register. W register we can find parallel with accumulator in the other form of microcontrollers. W is a working register in PIC microcontroller, which is used as a source or destination for any arithmetic and logic operations. Then, as you can see, you have 3 timers: timer 0, timer 1, timer 2, with different prescalers. I'll explain you what is that. And it has a serial port and USART, and also an analog to digital conversion unit. It has 5 ports and 33 pins of input output lines, so which can be individually programmed as either input or as an output port pin. And so this is basically an overall. Apart from this, you have a parallel slave port used for parallel communication. So this is basically an overall overview of your PIC microcontrollers architecture. So as I said, whenever we are programming using C language, the architecture takes a backseat. We don't need to bother much about architecture. We just need to bother about its feature. But whenever we are dwelling within the assembly language, we have to put a lot of value to this architecture, because we have to know each register, their name, and how many bit wide they are, so that we can program correctly. So that's the basic block diagram or the architecture of PIC microcontroller. Let's move forward. These are the features of PIC microcontroller. They are called high performance RISC CPU. RISC CPU is nothing but reduced instruction set computing. Reduced instruction set computing is nothing but it's a family of microcontrollers which try to execute every instruction within one cycle. That is what is called as RISC based processors or controllers. As you know, it has a very simple instruction set. There's just 35 single word instructions, and all the instructions except for few branch instructions would be executed within one cycle in PIC microcontrollers. It can have a maximum operating speed up to 20 megahertz clock, and it has an internal RAM and a ROM. The capacity varies from family of different family of microcontrollers. It has up to 12 interrupts. It has a 8 level deep stack, as we discussed. It has a power on reset option. It has power up timer option. It has oscillator startup timer option. These are different timer and power options integrated into PIC microcontroller to give you greater flexibility in programming and usage of your microcontroller. It has a watchdog timer operation, which can help you to detect any program malfunction in the microcontroller. It has a program code protection option whereby you can write a program and lock it so that nobody reads a program or alters a program on a later stage. It has a power saving sleep mode, as you have a sleep mode on your computers or desktops or your PCs or laptops. The same way you have a sleep mode on your microcontroller, which can be set at your command. It has different type of oscillator options. As I said, you can select a low cost RC oscillator or a high cost but stable crystal oscillator also for your big microcontroller operations. And it can operate on low power. It can operate on a very wide operating voltage range from 2.5 volt to 6 volt. Each pin on your big microcontroller can bear a load of up to 25 milliampere. And it has commercial and industrial extended temperature ranges, which makes it feasible or flexible to be used either in commercial or industrial sectors. It has a very low power consumption compared to many microcontrollers out there. It is less than 2 milliampere at 5 volt and less than up to 15 microamperes at 3 volt. So that is a very low power consumption comparatively. So these are some of the key features of your PIC microcontroller. And some of the peripheral features, as we'll notice with PIC 16C7 series of microcontrollers, is that it has 3 timers: timer 0, timer 1, timer 2. Timer 0 is 8-bit timer, timer 1 is 16-bit timer, timer 2 is 8-bit timer. Now these timers or counters, as you know, timer is something that counts the internal events and counter is something that counts the external event. Your timer 0 is actually coming with an 8-bit prescaler. Now what is a prescaler? Prescaler is how you divide your clock frequency, and it gives you flexibility in counting speed, in setting up the counting speed. Now timer, it counts an event, but how fast should it count an event? It depends upon the prescaler value. Now that differs for each timer: timer 0, timer 1 and timer 2. As you see in timer 1 also you have a prescaler, but it's a 16-bit timer, and it can be incremented also during sleep mode, timer 1. So timer 1 can be used for even real-time clocks, as you know, your system clock or real-time clock. Even when the computer sleeps or is shut down, it is running. So timer 2 is an 8-bit timer counter with 8-bit period register, prescaler and post capture, compare and pulse width modulation module. Now all these are different options to capture your events or record your events, and also pulse width modulation is actually uh, to create a type of square wave to operate motors. It is very useful for interfacing motors and operating them at varying speed. So pulse width modulation module is also possible with timer 2. Timer 2 can generate the frequency for that. Um, your PIC microcontroller can capture up to 16-bit maximum resolution. It can have 12.5 nanosecond, and of course its pulse width modulation can have a maximum resolution of up to 10-bit. 10-bit is nothing but 2 part 10 bits, so that's 1024 resolution it can have. Now 8-bit multi-channel analog to digital converter it has. So it has an ADC of 8-bit, and there are 8 multi-channel. Now how many channels? It depends upon the family of microcontroller. It has a synchronized serial port, a serial peripheral interface, and I2C interface. It has a universal asynchronous receiver transmitter module on board, that is nothing but your serial communication interface or USART interface, that is on board of your PIC microcontroller. It has a parallel slave port with external read, write, and clock select pins. It has a brownout detection circuit for brownout reset, as I mentioned already. Brownout is nothing but whenever your microcontroller falls below the minimum voltage level or operating level, your microcontroller automatically shuts down or suspends all activity. So that is what is called brownout reset. So these are some of the features, peripheral features of your PIC microcontroller. So let's see some feature comparison with the family of microcontroller. Now, what we are interested as far as the scope of our subject is concerned, or this course is concerned, is PIC 1674A. As I have marked it in yellow over here, that is what we are interested in. So you can see the program memory, it has is 4 kilobytes, data memory, it has is 192 bytes, input output pins, it has is around 33. Does it has a parallel slave port? Yes. Does it has a capture, compare, pulse width modulation modules? Yes, it has 2 of them. Does it have timer modules? Yes, it has 3 of them. It has 8 channel analog to digital converter. It has a serial communication facility with serial peripheral interface or serial communication interface, or I2C interface, and USART. It can be programmed in circuit serial using in circuit serial programming. It has a brownout reset, and it has an interrupt source. It has 12 interrupt source in fact. So these are the basic features, especially of PIC 16C74A PIC microcontroller. Let's move ahead. So as far as program memory is concerned, your PIC family of microcontroller comes with either 2K or 4K addresses of program memory. So you can access either the 2K or the 4K variant. Now, to access 2K, you require 11-bit program counter, and to access 4K, you require 12-bit. But the PIC family has given you up to 13-bit program counter, so you can access up to 8 kilobyte of addresses. So, as you can see, your program memory is actually allocated for the main line of the program or your main function, and your interrupt service function, and your end of code or tables. Your program memory is basically bifurcated, or it's actually divided into this different sections. So this is how your program memory is divided. Now PC lath is actually a bit, okay, and it is set or cleared whenever you're accessing a 2 kilobyte memory or a 4 kilobyte memory unit. As you can see, PC lath 3, that is PC lath, has actually 4 bits, so its third bit is set to 0, or its third, or actually the fourth bit. The fourth bit is either set to 0 or set to 1, which makes a difference. That is, whether your microcontroller is accessing a 2 kilobyte memory or whether it is accessing a 4 kilobyte memory. So that is what is a PC lath bit. So it is cleared or set whenever you access 2 kilobyte or 4 kilobyte memory units subroutines. So yes, so that was about program file structure. Now register file structure and addressing mode in your PIC microcontroller. We can see uh, in PIC microcontroller, register file is to denote locations that an instruction can access via address. That is what is a register file basically, and it consists of 2 types of components, that is general purpose register file and the special purpose register file. As you know, general purpose register file is basically the RAM memory where you can read or write any data to. So, and the special purpose registers are the specific registers used for configuration. For example, to configure your timer, to configure a serial peripheral interface, to configure an analog to digital conversion. All these requires a special function register. So that is what a special purpose register. So basically, your register file structure in PIC microcontrollers are divided into general purpose registers and your special purpose register. So you can see the divide of it. There are 2 register banks, bank 0 and bank 1. Both are 128 bytes wide. Now this is what I'm talking about. Now 128 bytes are divided to special purpose registers that you take up to 32 bytes, and the RAM takes around 96 bytes in bank 0. And bank 1, as you can see, special purpose registers occupy around 32 bytes. The RAM occupies only 32 bytes, and extra RAM is dependent upon the type of microcontroller family that you are going to choose. And of course, the address spaces are denoted with hexadecimal codes. Only can access the address space. So register file, a structure, and addressing mode. Now, most of the instructions in my PIC microcontroller employ the direct addressing mode, and it uses only 7 bits of instruction to identify a register file address. Now, the 8 bit of the register file address must come from a separate register bank select bit, which is called as RP0. Now, as you can see, because of this, most of the registers in your PIC microcontroller can have a dual address, or the what you say, the critical registers that are in use in PIC microcontroller can have two addresses based upon your RP0 bit or the register bank select bit. That is your RP0 and RP0 bit can be 0 or it can be set to 1. So when it is set to 0, you have an address 14 which is the effective address for the status register, and if your RP0 bit in status register is set to 1, the effective address will be 94, which is kind of two different banks. So to employ this direct addressing mode, you actually have two addresses for some critical registers. So for indirect addressing mode, you have to write a value into your FSR register. Now FSR register is accessed either at two of these addresses, that is H04 or H84. Either one of these addresses you can access FSR, that is whenever you write a value there, you write into this register FSR. And whenever you write a value into FSR, only it will help you to program an indirect addressing mode. Indirect addressing mode, you know that it is an addressing mode where you have a value in a register which is a reference to an address where the value is actually present. Okay, so that is what is indirect addressing mode. Now there are different CPU registers. Now one of the CPU registers that you need to notice is working register W. W is the working register, which is an 8-bit wide register. Now you can draw parallel between W register and your accumulator that you have seen in various microcontrollers. W is the register that is used as source or destination for various manipulations, whether it's arithmetic, logic, or bit level or byte level manipulations in PIC microcontroller. And the other register that your CPU or PIC CPU has is called as a status register. You can draw parallel between status register and the flag register, which you would have seen in most of the microcontrollers that you have studied till now. Now the status registers, as you can see, the most significant bits to the 7th bit and the 8th bit and the 7th bit do not have any functionality. They are 0. They are kept for future use. The 5th bit is actually the RP0 bit or register bank select bit. We saw its use just some time back, and the next 2 bits are used for reset on power status. And the next bit is a 0 bit, which is set or reset based upon the value of a register in the RAM or your working register. Whenever the value there becomes 0, the 0 bit is set. DC is digit carry bit. You can draw parallel between digit carry bit and auxiliary carry bit. You know what was an auxiliary carry bit? Whenever the lower nibble had a carry to a higher nibble, then the auxiliary carry bit was set. And this is the same function of digit carry bit. Whenever the lower nibble has a carry that will carry over to the higher nibble, digit carry bit is set. This is basically used to deal with binary coded decimal numbers. And you know the carry bit, whenever there is an arithmetic overflow from the most significant bit, then the carry bit is set. In an event, this can happen in an event of addition as well as subtraction, where a borrow can happen. In fact, when a borrow happens also, your carry bit is set. Yes. So the other registers are FSR, As I just discussed some time back, FSR is a register which is used to write a value for indirect addressing mode. So whenever you write a value into it, it is actually a reference to an address from where we can access the data. If you remember data pointer concept and register HL concept in the microprocessor 8085, then you will be able to understand what is an indirect addressing mode. INDF is another register which is used to access the location pointed to by the FSR. So these are the different CPU registers being used in PIC microcontroller. The other CPU register that is used is your program counter. The program counter is 13-bit wide. Your 8 bits are actually your PCL, and the address of that is H02 to H82. The higher 4 bits, or the most significant 4 bits, are actually called PC-lath, uh, which is actually, we saw its functionality. PC-lath 4 bits can actually decide the accessing of your 2 kilobyte or 4 kilobyte memory. As we can see, your PIC microcontrollers has an 8 level stack. So whenever a program counter is dumped in an event of a jump instruction or branch instruction, your program counter is dumped into an 8 level stack. So up to 8 interrupts can be serviced at any given time. So that is what, these are the CPU registers that are available in your PIC microcontrollers. So these are the CPU registers. We saw about the register files, and we saw the basic block diagram and the variants that uh, uh, the PIC microcontroller has in its family. So that is what we studied in this lecture.